All right, welcome to the illustrious Lake Wabisa field site. This is one of two sites that was put together by one of Gene Barr's students, Todd Rain. And the overall purpose of this site was to look at this till underlying a lot of Wisconsin. And the reason for the study here was basically that the current landfill of Madison was running out of capacity, and they were looking for a place to put a new landfill. And we're talking about putting that landfill over the till with the idea that it would act as a confining unit. And so the question that Todd wanted to ask was, how good of a confining unit is this aquifer? Is it reasonably homogeneous and reasonably low conductivity such that it should block any contamination from getting down to groundwater? Or are there holes or lenses through that confining unit that would present a pathway for contaminants? So we're standing here right next to the central well, and if you look at the very back page of your lab, you'll see this diagram here showing you the arrangement of the well field. This direction off that way is north, and so I'm standing right next to this 4-inch well at the center here, which is where he was able to do a pumping test. The other page you'll want to turn to in your lab is the page that looks something like this, which shows what's going on with this series of piezometers that's surrounding this central well here. So each of these piezometers is drilled to a different depth, and they're only screened at the very bottom of their interval. So for instance, this well here is PVC, and it goes down to a certain depth, and at the very bottom it has a 1-foot screen. So it's really a piezometer, it's not a well. So by doing that, Todd was basically able to run a pumping test at this well, look at the response at all of these surrounding wells, and if they basically appeared the same, that tells you it's pretty homogeneous. If he saw differences in the drawdown change when he was pumping, that would imply some sort of heterogeneity that you should be careful of. Now, I'll walk off this way a little bit, and you can see these yellow trees off in the background that way. There was a second version of this site that had the same central 4-inch monitoring well and then a bunch of piezometers around it so that they could test heterogeneity at 2 scales. That way they could look all the way over there and say, if I do a pumping test, do I get the same results or do I get something slightly different? So what we're going to do today is a bunch of different tests using a bunch of different tools, and we're going to focus on a pair of piezometers where one of them is fairly shallow and one of them is fairly deep. And so I'm standing at the 4-inch well here. I'm looking north, so I see those would be wells 8 and 9. And what I'm going to do is I'm going to go over to these wells right here, and this should be well 17 right here, or piezometer 17, and this will be piezometer 18. And that's where we're going to do the majority of our work today and take a bunch of measurements. So you're going to need some numbers from this table here, for example, things like where the elevation of the top of casing is in order to convert what we're going to measure, which is depth to water, into hydraulic head. So without further ado, we'll get into some of the testing tools that we're going to use, and we're going to show off both measuring water levels, measuring things about the fluid chemistry, and then we're going to end with a slug test, which is a way to back out the hydraulic conductivity of an aquifer. All right, so the first piece of water level equipment that we're going to demonstrate here is what's known as a plopper. So a plopper is really just a steel weight that's got a little concavity on one side, and when that hits the water, we're going to hear it nicely in the well. Now, with these plopper tapes, you can tell basically what we did is we took a measuring tape and we just attached it on the end here. And so there's going to be a slight correction we're going to have to measure to figure out how much extra length we've added by adding this plopper. So I'll start out by doing that here. And what I'm going to do actually is I'm going to go to a meter, and then I'm going to see how far beyond 2 meters the plopper goes. So if I measure it out, the plopper goes to 2 meters and 5 centimeters. So this extra length added is 5 centimeters. So now I'm going to send it down the well, and you might be able to hear it from far away. If not, we'll get some better close-up footage. But I just send it down the well and listen for a plop like that. And when you're honing in on your depth, what you want to do is actually get your finger right near what you think the value is and slowly go a little bit more until you just barely get it plopping like that. The next piece of equipment we're going to demonstrate is what's known as an electrical tape, or E-tape. And this has got a little connector in there. So basically what this is right now is it's a broken electrical circuit. It's two wires that run down either side of this tape. And when water hits this sensor here, as long as it's got enough dissolved solids in it, it's going to complete the circuit and you're going to hear a beep. So a few pieces of advice if you want to look like an expert using an E-tape in the field. A lot of E-tapes have this little rubber stopper here that's meant to slow this down, but if you run it with this the whole time, it makes this really annoying sound the whole time. So good idea to loosen that as you're sending it down the well. Another piece of advice is make sure you turn it on and make sure you turn it off when you're done. So most E-tapes have a switch like this here, and then they've got a test button. In this one, it's kind of broken off, but it's off now. I turned it on, and this test button, if you press it, you'll hear the beep, which is going to be the same thing we hear when we sense water down the well. One other thing to note on this, when you're measuring the water level in this well, there's no correction needed because all measurements are from this point where the circuit is going to be completed. So if you're measuring water level, you can go ahead and just read it right off the tape. You don't need to make a correction. When you do need to make a correction is when you're measuring the total depth of the well, because this is going to be what hits the bottom of the well, and so you need to figure out how much extra length you need to add when you hit the bottom of the well with this. One other little piece of advice when using these E-tapes, try not to drag the ribbon against the edge of the well like this, because that's going to pull off this plastic and make it so that these wires can touch water, and we don't want that to happen. So generally you want to hold it somewhat above the well as you send it down. And when you get to water, you should hear a nice loud beep. There we go. So now, just like with the plopper, what we want to do is sort of get our fingers right near the measurement location so we can really hone in on what the depth is. And when we do that, we see that we are at a bit beyond 50, so 51, 2, 3, 4, 5, let's say 56, and that is 1 meter and 56 centimeters. All right, so now we can measure the depth to the bottom of the well. So here's another way to avoid looking like a newbie in the field. Do not send your E-tape all the way down the well to the bottom and leave it on like that, because nobody likes listening to that tone all day. So we're gonna turn that off. And then we're just gonna, again, send this down until we feel the line going slack. This is a little tougher. Say right around there is where the device is going slack. So it's 31, 2, 3, 4, 5, 6 centimeters. This tape has a precision of 1 centimeter. And so it's 9 meters. So 9 meters and 36 centimeters to the bottom of the well. Last piece of advice is, as you're pulling your E-tape up, you want to sort of bring your E-tape spool to the top of the well. You got this nice foot you can rest on here. This will keep the cord from rubbing against the well as you bring it up. And then always be sure to be careful when you get towards the sensor, because you don't want to bang it against the side of the well and break it. And there we go. So the next tool we're going to demonstrate here, this isn't for water level measurement. This is for getting a little bit of a sense of the water chemistry. This is a conductivity meter. And no, unfortunately, it's not a hydraulic conductivity meter. You can't just measure hydraulic conductivity easily in the field. It's an electrical conductivity meter. So we're going to send this down the well, and we want it to be measuring the electrical conductivity of water that is basically right at the well screen, because all the other water in this well has probably just been sitting here for a long time. It's stagnant. It's not as representative of the local groundwater. So I'm going to send this down to basically where I felt the bottom before. I'm going to pull it up about 6 inches so that it's out of any muck that's at the bottom of the well, and then I'm going to take a measurement of conductivity. So I'm going to set that down for a second and send this guy down. And through the magic of Hollywood, we knew how much cord length we needed. So right about there is where I'm feeling the bottom. I'm gonna pull it up, just say 6 inches or so, and then I'm gonna take my reading. And if we can get a zoom in here, what we'll see is the readings on this meter. It's gonna tell us a bunch of different things, only really 2 of which are different. So it's telling us conductivity in a lot of different ways. So you see it says 478 conductivity in microsiemens per centimeter. That is the conductivity that this meter is reading right now. It's reading the electrical conductivity, which is a function of the total dissolved solids and the temperature of the water. So the other measurement that's a little bit more important that we'd like to use here is the corrected conductivity. And what that does is that gets rid of this effective temperature and treats the water as if it were at 20 degrees centigrade. So this number here, this 649, that is representative of what the conductivity would be if we warmed this water to 20 degrees C. And so in that case, we're just measuring the effect of the total dissolved solid. So this is really the more important measure for our observations. Notice, as usual, groundwater tends to be fairly cool relative to the surroundings. So we're only at about 10 degrees C. So the last thing we're going to do out here, and this is going to be data you're going to use to try to estimate the hydraulic conductivity of this till that we're sitting over, is we're going to do a slug test. And so this is the fancy slug here. Basically all it is a piece of solid plastic with a given volume. So we're going to send this down the well. We're going to put it below the water level and actually pretty deep. We probably won't let it touch the bottom, but we'll get it pretty far down in the well. And what we're going to do after we get this down in the well is we're going to look at how the head has changed and then watch as it decays back to its static water level. So what should happen, if all is right with the world, is we'll put this slug in. That's going to displace water and raise the water level in our well. Then the fact that our well now has a higher head than the surroundings is going to cause flow out of the well, and we're going to get a decay, something that almost looks like what we saw with the falling head permeameter. So to do a slug test, we need to know the volume of this slug we're putting in. So we're going to want to get the diameter of the slug, which in this case looks to me to be about, I would say, 22 millimeters or 2.2 centimeters. And then we're also going to need to get the length of this slug. This is kind of a long one here, so I'm going to start at the 1 meter mark here. Put that right there. And then measure it out. And let's see if I look good on both sides. So I'm getting a measurement of 1 meter and 52 centimeters. So 1.52 meters for the length of the slug. So we'll show you some video of Chris and I working together collecting data after a slug test. One thing to keep in mind with a slug test is once the slug test starts, you can't stop it. So once this is in the well and we've displaced the water, we've got the system in a transient state where the water level is decaying, you can't just pull the slug back out and then start over, because it'll still be sensing that prior injection of mass into the aquifer. So it's really important. Often with a slug test, you want to have 2 people there, one who's sort of controlling the slug and collecting, writing down the data maybe, and the other person who is taking measurements, usually with an E-tape to get pretty accurate measurements. So we'll demo a little bit of that, and we will provide you with the data from this slug test to analyze in a later lab. Just tell me when we're at 15 seconds. Let it rip. Last little bit of bonus footage here. So once you've done this, or I guess at least seen a video of it, you can say you've seen groundwater sampled. So this is what's known as a bailer, and unlike the slug, this is a hollow tube, so you can see through the end of it. And what it's got is it's got a ball valve on the end of it. So when I push this down into water, when it falls, water's going to go up past the ball valve. When I pull this back out, the ball valve is going to keep it closed, and so it's going to trap this much water in this bailer here. There's a lot of great sort of ball valve type well technologies. Here's one for your bloopers reel right here. And a lot of them rely on this ball valve and use it to pull water out of a well. I think of this as one of my like zombie apocalypse ways to get clean water if I need to. So all you do is send it down to a well, get it below the water level, and now I'm going to pull it back up, and notice it is full of water. So if I wanted to sample groundwater, that'd be one way to do it. There are some tools, like one pictured in the front of your lab, that'll actually allow you to lower a sampler to a specific depth and then open at that specific depth so that you can sample water quality at different locations, different depths within a well. But again, one more time, why not? We've got a lot of noise here. There's the bailer going in and the water coming out. And there you have it.